Okay, hi everyone. Today we talk still a bit more about differential forms. It's really a strange sound. Okay, so we talk a little bit more about differential forms. I will tell you a bit more how they look like in charts and like in local coordinates, how to write them. We learn a little bit how to calculate with them, and then at the end we will talk about how to integrate over a differential form along a curve. So that was one of the motivation why we talked about differential forms in the first place, is because we want to integrate certain things along curves, and then next time that will be like one form, something that you can integrate along a curve, and then next time, or maybe still at the end of today, we talk about differential two forms, and that will be two like things that we can integrate along a surface, or like part of a surface. So maybe I recall where we stopped last time, and that was the definition of a one form. So a one form is a family of linear maps, and the family is indexed by points of S. So what you get is a linear map for every point of your surface. And what it does is like it assigns to every tangent vector a number in such a way that it's linear. So that means that if you scale the vector, then you also scale the number that you get. And if you add two vectors, then you also add the numbers that you get. So that's like what is the linear. So it's you can think of that as like some way to measure like vectors at points of the surface in a certain way. And if you want to visualize it, it's the best practice is to think of that as like a certain number of planes which are parallel, and then the evaluation of the alpha with a vector at that point gives you a certain number, and that number is the number of intersections of that vector with these kind of planes. So that's one way to visualize it. Sometimes it's helpful, sometimes not. Depends a bit. Yeah, so that's the definition. And as a first part, I would like to discuss how the differential forms look like on an open subset. So just if you have like a sheet of paper and it's not curved at all, how do differential forms look like here? That's like the simplest case, and then later we will talk about what happens if you curl it and how to describe them. So we start with the simplest case of an open subset and consider that as, again, as a surface. So we fix a point in the open subset, and we have seen last time that every tangent vector at that point is just given by two numbers, namely as v equals to v1 times dx plus v2 times dy. And yeah, sometimes I denote, like I write explicitly that there's a point where we have to take the value. So either sometimes you consider dx as like really as a vector field, and then I need to specify the point, but most of the times I'm just too lazy and will just like write dx, and then you have to guess from the context of the formula where that tangent vector is like taking value at. So it's really just like that you have a certain point and a vector, and then you have projections onto on the canonical axis, and these vector fields which are like dx, which are the unit vectors in that direction, dx and dy, and then this projection dx and dy as like the unit vectors, then this projection is just v1 and v2. And we mark dx and dy as just like a notation because we have like we write points usually as x and y. But sometimes it's also more useful to use different kinds of coordinates. For example, I could like have the coordinates where it's phi and r, so like polar coordinates, and then I would probably most likely also write that as dr and d phi if I think of that as like say plus infinity times something like that. Then I would have like the coordinate here would be called r, and that would be phi. And then of course these unit vectors would be something that points like outside in the radial direction, and d phi would be a vector which points in the phi direction. So just so that's like just like a notation that it's like dx and dy because usually we have like x and y coordinates. Okay, but that's like so much about like the tangent vectors, and now we want to talk about differential forms. So assume for now we fix one point, so we just have like one particular point. Be a linear map. Because it's linear, so we want to calculate alpha p evaluated on V. And since alpha p is a linear map, we can just plug out these numbers. So we get like so that's just using linearity. So what you see is that this value of the linear map on the vector V is completely determined by essentially these two values. Everything else is like just like the V1, and the V1 depends on the vector. But like if you know these two numbers, then you know alpha p of every vector. So that's the upshot of this little calculation is that alpha p on a given vector is completely determined by linearity by the two numbers. Which will be alpha p evaluated on a vector dx and alpha p evaluated on y. And I will call these numbers alpha 1 and alpha 2. So these are just two numbers. Like for every fixed p, I just get have a certain vector and I plug that in alpha. And if you want to think of that as in terms of these planes, what you have is you have a certain that's the alpha again, the alpha p here. So p is here. What you then do is you draw dx, which is a vector here, and you draw dy, then so you draw these two vectors, then alpha 1 is the number of intersections of the alpha of the planes with dx. So that's alpha p dx, the numbers of intersections that we have here. And similarly, you get certain intersections with the y, and that's given by alpha p dy, and that's just alpha 2, and this one alpha 1. So these two numbers, they have like just like the interpretation. You draw alpha and then just look at like how often they intersect the unit vector in the x direction and how often they intersect the vector in the y direction. And then these are these two numbers. So we see that every linear map at a given point P is completely determined by two numbers. So it's like determined by alpha 1 and alpha 2. So that's very similar to a vector at like one point, which were also determined by two numbers. Namely, one of them was the amount in x direction, and the other one was the amount in y direction. So the amount of information is the same. It's like, again, two numbers. But the character is different. In this one, the vector is just really like the coordinates of an arrow. And here, it's in some ways like the coordinates of planes. So it's like geometrically, it's something different. But it's, again, two numbers. And these numbers, alpha 1 and alpha 2, are called the components of alpha. So similar as for vectors, where we also call them the components, we now have the components of the differential form at that given point. And there's a different. So hopefully it's better now. So there's a different way to think of these components, which is very similar to this description that we have v1 dx plus v2 dy. And something similar we would like now to have, but instead of v1 and v2 and v here, we want something like alpha equals to alpha 1 times something plus alpha 2 times something. Similar description for alpha in terms of alpha 1 and alpha 2. And for this purpose, we define certain standard differential forms. So we define the one form, which is called dx. And dx is a map, again, from TP dn. So that you really should think as a notation. It's not like something that you can take out. You can also call that just like some name that you prefer, for example, beta. But you will see in a second why dx makes sense. But we really just consider that as a name for the object that we define. So dx is something like as a one form, and as we have seen over there, every one form is completely determined by the evaluation of like the value when we plug in dx and when we plug in dy. So we can completely determine dx by these two values. And the way we do this by we say that once it hits dx, it gets the value 1, and if it hits the tangent vector dy, then it gets 0, and then, of course, we want this to be linear. So every other vector, we just extend it by linearity. So that's a linear map that we define that way. And similarly, we define dy dp as the differential form where we just change the equations. So that's dy on dx is 0 and dy on dy is 1. So that's exactly of that form, right? Like it's a map that eats tangent vectors. It's linear by definition and has certain values on a characteristic vectors. So for the people that know a little bit of linear algebra, just one side remark. If people like don't know what is going on or like the words don't make sense for you, just don't get confused. That's like an additional remark. What is happening is that dx, p, and dy, p are the basis of the tangent vector. So that's saying that essentially that every vector can be written in a unique way as a linear combination of these two elements. And there's something that is called a dual basis. Which are a basis in a dual space. And they are characterized essentially by equations like that. So if you know that, then you might recognize that from your linear algebra course. Otherwise, forget what I said. So the point was, that we wanted to find like a description of alpha in terms of alpha 1, which looks very similar to the vector things. And the way we do this is we can really write that alpha p equals to alpha 1 p dx p plus alpha 2 p dy at p. So here I really emphasize that these alpha 1 depends on the point. So I should have maybe written here already alpha 1 of p, because of course the right-hand side depends on p. So we have this equation also, I claim. So we have to check that equation. Check this equation. So what we have to check is that if you want plug in dx and dy, then we get the same result from the right-hand side and from the left-hand side. So we say we plug in dx. What happens is that we have to plug in dx here. Or maybe I do one very slow. And then, so what happens is that dx on the partial x gives us 1 by definition of dx, and the dy evaluated in dx, it's this equation here, gives us 0 by definition. So what we end up with is that this one is alpha 1 at p. And that was, I think I'll just switch that off. So what we see now is that alpha p evaluated on x equals alpha 1 of p, but that was exactly the definition. So we saw that the left-hand side coincides with the right-hand side when evaluated on the x. And similarly, we get the alpha y equals, and then a similar calculation, and then we get at the end the alpha 2. So that checks that like the differential one forms, if you evaluate it on both sides, you get the same result. So like that checks that we get really this description of the one form in terms of alpha 1 and alpha 2. So the summary is that every differential one form alpha on an open subset R2 is of the form we say that alpha p equals to alpha 1 p x p alpha p. For functions on which actually turn out to be smooth, for smooth functions where alpha 1 and alpha 2, just like smooth functions on an open subset. So if you have like two functions, you can define a one form exactly by this equation. Okay, it's just say like alpha 1 and alpha 2, and I use these functions as the coefficients. And conversely, once we have a one form, we can evaluate the one form on the x and then the y and get like certain numbers out of that. And these ones will be these functions alpha 1 and alpha 2. So there's like essentially on an open subset, there's no difference between differential one forms and like two functions. Once we have these x and y. And usually it's a bit cumbersome to write like this p all the time. So we just leave it out and write in short. It is write like alpha equals to alpha 1 dx plus alpha 2. So you really should think that this is just like just notation, where you really need to like for every point p, here there is a right hand side and a left hand side in p to get the mean. Okay, so so it's nothing really like crazy or like scary. A one form on the open subset. The nice part is that this definition of a one form also makes sense of like something curved. For open subset, it boils down to just having two functions on the open subset, so of x and y. And in a little bit we will see that that's of course like a description on something like uncurved. And if you curve it, then there will be also like a relationship which also gives you a one form on the curved object in terms of functions, but like the expression will be more complicated. We don't have like dx and dy, but something more complicated because we want it, of course, to be like defined on the tangent space of the surface. But before we discuss that, I would like to first describe a little bit more this kind of objects that we see here. That we have a one form, in this case it's called dx, and we plug in a vector field. And that's something that happens quite often, and it gives you always a function. So I would like to describe that function a little bit. So we are back to the setting where S is some surface. Suppose that we have x, which is a vector field on the surface. So that means for every point of the surface we have a tangent vector at that point. And suppose that alpha is a one form on S. So that means for all P on the surface we have two data, namely x of P, which was the equation of the vector field on P, which is a tangent vector at that point. And we can evaluate the one form, which is a map from tangent vectors to R. So what we can do, of course, is now to plug in xp into alpha to get some number. So we can plug these ones in, and that gives us a number. And then we want to consider that as like as a function of p. Means that times a function on S. It is denoted by alpha. Usually spoken as like saying that alpha is paired with x, where x is like plugged into alpha. But one of my professors said x eats the alpha, or alpha eats the x. And the function is defined by, that's a function on S, and it's just saying that alpha p. So you have like a point, you define this function alpha of x, which is a function on the surface, by saying like at some point, what I do is the natural operation. Maybe say we evaluate the vector field at a point to get the tangent vector, and we evaluate alpha p to get like a linear map from the tangent vector to R. And what we do is then just plug this in to get a real number. So it's mostly notation, huh? Now, of course, you can see that this is what is happening here. You can like see dx as a one form, and then plug in the dx, for example, that gives you the function, and that function is like the function one in that case. So it's a constant function. Okay. So we now need to look at like ways to construct differential forms, or one way, or like one way to, or like discuss certain ways to get like the differential one forms. One way we already saw it was like two functions on an open subset. We know that construction, but there's another example which is really important. And that's if you have like a function on the surface. So, look at the function on the surface. Surface. we saw last time that the directional derivative gives us a map which was denoted by Tp of f, which was a map that eats a tangent vector and gives us a number. And actually we saw last time already that this map happens to be linear. So you can view that as a differential form. For every point P, we get a linear map that assigns to a tangent vector a certain number. So it might be it's like just a matter of notation, but usually if you want to view this directional derivative as a one form, usually people write this as df instead of tf. It's denoted by df. So df is again, you can think of that really as like it's a pair. It's really like a differential form. And so what this means is that df at the point that one eats a tangent vector because it's a differential one form. And the way it is defined is that we say that we take the directional derivative of v with respect to f to get a number. So it's like essentially the same data as like the directional derivative. It's just that people prefer to write df instead of tf. And it's a bit of a choice, but like it comes inspired from this kind of definition, where we say like x and dx, we want something similar for df, and we will see in a second why this notation is actually quite nice. So maybe like you want to think of that function as like giving you a height of certain mountains. You have a mountain, and you can think of this function as a function that describes you the height of the mountain. And then you get like a certain level set, if you look at like the contour of the mountain. And you now have a vector at a certain point. You write this as v, then df at that point, p, derivative of f. It's a directional derivative of f, so it's a measure of how much f changes in the v direction. Or if you think of that in this picture, it's in the first approximation you can think of the level set or like the contours as like really as like a family of planes. You can think of that as in first approximation as a planes, and then you that's the number of like intersections with the contour plane. So how many contour lines intersect. is df at that point. So you look at the contours of f in the neighborhood of p, and then if you look at like a small enough surroundings of f, you just get like a staggering of planes in first approximation. Okay, of course, like if you look at like higher versions, then they get like curved a little bit, but in first approximation at a given point, you just have like a family of planes. If you look at like you stand there at the mountain and you look downwards, then you see like essentially that it goes like straight, and then you just like say how deep I go. That's like will tell you then how often you have like these contour lines. Let's say like okay, now I drop 10 meters and another 10 meters. So that will be a more or less a linear way that they kind of like look like in the first approximation. So these ones, the contour lines will be df, and then the evaluation of f of that one form on the vector is just like calculating how many lines I'm hitting if I go in that certain direction. So that's the geometric interpretation of this one form df. So let's go back to this setting where we had something on an open subset, and let's investigate what a df is looking like in the case when we have an open like a function on defined on an open subset. Example, we look at an open subset, and we want that function is defined there. We consider again the open subset as a trivial surface. And now we saw before that a differential form, in particular df, so differential one form on d is completely determined by the components, right? So we evaluate it on x, and maybe evaluate df on y. So these are two functions, and they completely determine df. So let's have a look. Let's calculate what these kind of expressions are. So we have df, and we plug in a vector here, and we get a function. So we have to plug in a certain point. So let's go very slowly by definition. So what we have here is a one form and a vector here that gives us a function, and we evaluate it on p. We just saw here what the definition of that is by here. We write the point on the one form, and we write the point on the vector field. So now that's like just like saying now df at a point, and for that we can use the definition. Maybe say this definition of the one form df in terms of the direction of derivative. So this means we get here p of f evaluated on the direction of dx. And we have seen last time that this one we calculated last time, for example, that this one is nothing else than taking the partial derivative of f in the x direction at the point p. So what we get as the upshot of this calculation is that df evaluated on dx is nothing else than df on dx. And Similarly, once we calculate df and dy, what we get is df partial derivative dy direction. So if you plug in now, like the knowledge that we had that once we have these coefficients, then we can write the one form in terms of dx and dy. So what this means is that if you take all of that together, is that we get the following formula. And that's a pretty important formula. So if you have smooth functions on an open subset, then this whole calculus boils down to this formula that you would like to write natively, right? Like if you don't think like too much about that, then you would say that df is something where we take the partial derivative in x direction, dx plus df dy dy. So it's a very natural formula, and sometimes you see that even like in real analysis courses, they just like you define that formula by just saying like, okay, like this, if you take the quotient, then you get the ftx or something. So it's like in some way, it's you can view it as like like a definition, or depending on like you can just like define the left hand side by the right hand side without really explaining the x and dy. But what we did now is like really give that geometric interpretation, right? Like what for us was like the very first starting point was to just realize, okay, we talk about tangent vectors, so that are vectors, and then we said like, okay, the x and dy are something that gives us 1 in the x direction and 0 in the y direction. So these ones were like really defined as one forms. These are not like formal something. It's really like a canonical one form that is defined on every open subset. And similar dy. And df as well was like completely defined in terms of the directional derivative, in terms of like taking a curve and then taking the variation. So all of that is like independently defined, and this calculation really shows that everything comes together in a way that you would expect it. And that's also maybe explains a little bit why I call these differential forms dx and dy and df instead of like something else, because I want like a formula of this. And this one is sometimes called the total derivative of f. Yeah. Okay, so to just give like a very concrete example, what it means is that, for example, if x is just the norm of the vectors, the norm squared of the vectors, and df, you take the partial derivative of f in x direction to get 2x dx plus partial derivative of y. That's really something that if you just write like here of that expression, what you would normally want to write. But for us, it's really like a concrete, like justified setting. What this kind of discussion should have motivated you to do is that even on an open subset, it's already quite interesting or useful sometimes to introduce like differential forms. So even on an open subset where you have like normal partial derivatives, so sometimes I need to think of that in terms of df and have the calculus of differential forms there. But what we essentially want to be interested in is not like something straight, but we want to talk about like curved objects. So let's go one step further and let's talk about the chart representation. And so the setting is the picture is the following, that we have a certain open subset of R2, and we have our curved surface, and we have a chart in between these two objects. So this one gives us a chart. And then what we have here now is we have over here we have like alpha, which is a differential one form that lives on the surface S. And we would like to understand that guy. So that's like something that maybe someone gave you a certain definition of, and you would like to understand that. And the best thing would be to understand it in terms of something. So we would like to define something over here, which is in the notation very similar to what we had last time, where we say we have a certain alpha here. And this one is then just a one form on the open subset, and that we can like write in terms of the coefficients as what we discussed right now. So the only question that we have to discuss now is how do we get from this one form of alpha and this map here that connects these two, how do we get like this one form over here? So that's the question for now. Say that alpha is a one form on S. That means that alpha p gives us something like this. And phi is a chart on S. And last time we discussed that once you have a chart, we get a certain map, which is the linearization of that map. So we get Tx of y of phi, which is another form of vectors now in the open subset, two vectors in S. We get this one for 4 points x and